Is circuits pretty much just a bunch of step functions?
Um, well, the way I use it, yes, but then I haven't taken like a classical circuits course in a long time. So before when I used to take it, there was also a lot about like Kirchhoff's rules.
Yes.
So like voltage rules, current rules, things like that. So
Physics.
mhm.
Cerritos looks like it might be the option.
Yeah, that's the option for most people, honestly.
Yeah. It's not terrible. It's like 40 minutes.
Okay.
Well,
Okay. At least the Cerritos College is right off the 91. And so
yes.
at least it's not too far from the freeway. So
Yeah. Maybe.
mhm. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Fantastic.
Good to hear. All right, so first thing, I'm sure probably what's on everyone's mind is the result of the poll. So it was quite close actually, or much closer than I had anticipated. So so the vote finally was maybe about 60% of the class voted for Tuesday, March 10th, and about 40% of the class voted to keep the exam date the same, Thursday, March 5th. But you know, according to democracy, we got to go with the one which was voted for the most. So midterm one has been pushed back to Tuesday, March 10th. Now the content of the exam is not going to change. So we are going to start some new stuff next week. But the stuff that we cover next week is not going to be on the exam. Today is going to be the cutoff. So after today, Everything that we cover after today, you can expect not to be on the exam. Okay. So content hasn't changed. In fact, I've already written it. It's just based on, the content that's on the study guide, the content that, we talked about last time. Okay. But the only difference is that, we're waiting a day to take it. Right. So please mark that in your calendar. Everyone that's on Zoom, please plan to be in class on Tuesday, March 10th, because that's when the exam will be. And that's the final change. Okay. All right. And so today, in terms of the lecture, the plan is just to finish up everything with Laplace transforms. So today's is going to be about impulse functions. Honestly, there's not too much with impulse functions. You'll see that impulse functions it's kind of a nice cool down topic. After kind of going really intense with all the partial fractions and the step function and all that stuff, impulse functions are kind of a nice break. And so we'll do that today. I anticipate we'll end kind of early, so I did bring a few more examples with step functions that we can go over as well. Just to kind of give you a more looks, right? So just like I've kind of told most people in the class that the thing with Laplace is that you kind of just need to get more reps with it. It's not something that you can just it's not something that kind of clicks right away. You kind of just have to kind of see more problems. And so I think seeing at least a couple more examples will help you guys with the homeworks and practicing for the exam course. Okay. All right. Any questions before we get started for today? I'll send an email to confirm the exam date too. I literally just checked it 5 minutes before the class because I kind of forgot about it. I was kind of busy today, but I'll send an email to confirm that the exam is pushed back. Okay. All right. So let's go ahead and get started. Oh. Don't know what's going on at the bottom of the screen. There we go. Okay. So the last topic in our Laplace section is about impulse functions. Okay. Okay. So what is an impulse function? So impulse functions are used to model phenomenon that only interact with your system for a very brief period of time. Okay. Hence the name impulse, right? So it's something that happens very, very quickly. Okay. Okay, so some examples that you might see. So, maybe you have a mass spring damper system that is struck very quickly, right? So we call that a hammer blow. Okay. Right. Another example from circuits is that, maybe you were looking to model the effect of a sudden surge in an electrical power. So that does happen, right? Especially in situations when, you're kind of tinkering with the circuits. And so being able to have guards against that is always good. So to be able to model it. Okay. Something kind of more specific, like we talked a lot about, shock absorbers or your suspension system in your car, going over a speed bump. Okay. Because a speed bump is only something that affects your car for a relatively brief period of time. Your car kind of jumps up and jumps down. Okay. And you can think of, lots of other situations. So basically, the thing that all these have in common is that they're only interacting your model for a very brief period of time. Oftentimes, it's very forceful, right? So oftentimes, it's a very large amount of force or a very large amount of displacement, but it only occurs over that short period. Okay. Okay. So how do we model impulse functions, or what do they look like? So mathematically, the name of the function that we use is called a Dirac delta function. Okay, so you might have heard that term before, maybe from a physics class. Okay, so a direct delta function is a function that is zero at all times except for one brief instant in time. Okay, so the symbol that we often give direct deltas is that they have the symbol delta, so that's a lowercase delta, and we say that it is a function of t minus a. Okay, now if we graph this out, okay, so we have our horizontal axis t. Okay, so at the given time that's specified by the direct delta, which is given by the value a. Okay, so let's say that the value of a is right here. Okay, so our direct delta is going to have a value of 0 everywhere except for when t is equal to a. And then when t is equal to a, the direct delta essentially has a value of infinity. Okay, so it's going to be 0, 0, 0, 0, 0. Then we hit a. It's going to spike up. Okay, in fact, it's going to spike up past the screen. Okay, and then come right back down to 0. Okay, so there's a piecewise definition for the direct delta. So we say direct delta of t minus a is equal to, okay, it's going to have a value of infinity when t is equal to a, okay, and 0 otherwise. Okay, so that might seem like a contradiction, right? So, how can we use a function that has a value of infinity? That seems like it doesn't make sense. Well, it makes sense from the fact that, even though here, right, I kind of drew it a little bit, maybe not honestly. So I kind of I drew it with some thickness, but the thickness of that direct delta is technically 0, right? Because that direct delta is only active for just a very brief moment in time. So even though it has a value of infinity, it's kind of balanced by the fact that its width is essentially 0. And so, one very interesting property is that if you integrate your direct delta as a function of time, okay, right? So you basically integrate it for all times, right? We basically define the direct delta in such a way that the integral of that is 1. So we do have a finite amount of area, that we do have a finite amount of function underneath, or a finite amount of area underneath the direct delta. It's just that, instantaneously it has a value of infinity and it's infinitesimally thin or small. Okay. All right. So now, of course, this is not a function that you can use for general math applications. This is another one of those, what we call engineering functions, just like our step function. Okay. So that's important to remember. This is not a traditional function. This is a very specific type of special function that's only used in special circumstances. Okay. Okay. And so you can hopefully see that, if you compare the list that we had above and thinking about what impulses physically represent in our engineered systems, you can see how this function is useful for them, right? Because just like how we understand impulses, direct deltas only occur for one brief instant of time, and then there's 0 everywhere else. And so they're perfect for modeling forcing functions that only interact for a very brief moment in time. Okay. Any questions on this so far? Yes.
Like you said, it goes to infinity, but does this also kind of scale down to say like a heartbeat rhythm that we see on the monitors like that? Because it doesn't go to infinity, but
yeah,
it has that jolt.
Yeah, that's a good point. So yeah, so mathematically, just to kind of maintain the fact that we have 0 thickness, we say that it goes to infinity, but realistically, it only jumps up to like a finite amount. But visually, that's a good kind of good analogy for that too, because those things, because essentially what you're modeling there is kind of the impulse of your heart kind of taking a beat as well, and so it's the exact same idea. Okay. All right. So how do we actually use this? So, So, of course, where we're going to go with this is that, we're essentially going to be using this with our Laplace transforms, because there's no other way to use this with our differential equations, right? And so to do that, we do need to compute the Laplace transform of our impulse function. Okay. So I'm going to use the term impulse function from here on out. So impulse function, direct delta function, they're interchangeable. They're used to refer to the same thing. Okay. Okay. All right, so let's compute what that is. Well, on the one hand, you could say that it's in the table, right? So if you've been using the Laplace transform table that I posted on Canvas, you'll see that the impulse function is there. So technically, you can just read it off the table. But this is actually a very easy Laplace transform to take. Okay, so let's take the Laplace transform of the direct delta or impulse function. Okay. So you have integral from 0 to infinity, e to the minus st, delta of t minus a, dt. Okay. Okay. So we want to find the value of this expression here. Okay. Okay. So to evaluate this integral, it's actually quite easy because there's another property of a direct delta function that we can make use of here. Okay. Okay. So this property of the direct delta is often called the selector property, right? And you'll kind of see why in a second. So if we take the integral from 0 to infinity of delta t minus a multiplied by another function of t, so let's say we multiply a function of g of t dt, okay? The result from this is the fact that we basically just evaluate our function g of t from at the location where the delta occurs. Okay, so this is equal to g of a.
Do that individually for every single impulse.
Yes, yeah. So every time you have an impulse, you would select a different value. Mhm. Right, and this makes sense, right? Because if we look at the figure or the drawing of our impulse function here, you can see that it has a value of 0 everywhere, right? So eventually, essentially, you can kind of break up this integral here. So we can say that this is equal to the integral from 0 to maybe right before a. So we say this is a minus, okay, of delta t minus a g of t plus integral of from a minus to a plus. So that's basically, a value right before a and right after a. Delta t minus a, g of t dt, okay, plus integral from a plus to infinity of delta t minus a, g of t dt, right? So outside of a, right? So outside of that very, very small interval from a minus to a plus, our direct delta is going to have a function of 0, right? And so that means this is going to be 0, and this is going to be 0, right? Just because that's how the delta function is defined, right? So only in that small sliver from a minus to a plus is that delta going to have a non-zero value, and then when you multiply that by another function, you essentially just get that function evaluated at that a. Question is,
what is the g of t function?
g of t is just some generic function.
Oh.
Yeah, so we can say g of t is just any function of time. Yeah, so that essentially we're going to use that to evaluate the Laplace transform. Yeah. Okay. All right, so knowing that property, we can evaluate the Laplace transform of the delta very easily because this kernel, or basically this part here that comes from the Laplace transform, this is essentially our g of t, in our property down here, right? So evaluating the Laplace transform of the delta, we essentially get e of minus s a. Okay, so essentially just plug in t is equal to a for the inputs. All right, so that's good because you know this e to the minus sa, you know, essentially this is going to end up just being a shift, right? And so you know we've kind of already been dealing with our second shifting theorem from our step functions. This is just kind of another branch of that, another application. Okay. Except it's actually going to be easier than step function. You'll see because you know there's nothing that actually contributes to the Laplace transform. It's just the shift. Okay. Okay, so that's that. So that's the Laplace transform of the impulse function. Any questions on this? Okay, so before we jump into an example, let's talk about the relationship between the impulse function and the step function just really quick. Okay. All right, so let me go ahead and draw the two functions here. All right, so first we have our step function. So this is u of t minus a, right? So we know what that looks like. At a, our function here is going to step up, just like that, okay? And then for our impulse function, for the same, we're going to assume that we have the offset be the same. Okay, so we're going to look at the impulse at t minus a as well. Okay. And so the impulse function looks like this, essentially just a straight line up that goes to infinity at that location. Okay, 0 everywhere else. Okay. All right, so what's the relationship between these two? And maybe you might see it already. Okay. Because if we look at our step function, remember, is a very unique function because, you know, essentially for most of the domain, if you look at the slope of our step function, it's 0 in most parts of the domain. Okay. Okay. Because we essentially have flat lines for most of the domain, so the you know, the derivative of a horizontal line is 0. Okay. The only place where the derivative is not 0 is at t is equal to a, right? Okay, so but at t is equal to a, we essentially have a vertical line that goes upwards. All right, and then so what's the slope of a vertical line? Vertical line has a slope of infinity. Right? So it turns out, you know, there's a function that has that exact same behavior, which is 0 at virtually every single location in the domain, except for one specific part where it has a value of affinity, which is our delta function. Okay. So this is kind of the really kind of interesting relationship between step and impulse functions. Okay. So basically, the time derivative or the derivative of your step function is equal to your delta function or your impulse function. And if you look at their Laplace transforms, this is actually very consistent with it as well, right? Because remember, we've been doing this for our Laplace transforms a lot, where when we take the Laplace transform of a derivative, right? Right. So let's say you take the Laplace transform of the derivative of some generic function f, right? So f here is just going to be a generic function, right? right? So we've been using this for all our Laplace transforms so far. So the Laplace transform of the derivative of f is s times the Laplace transform of f, okay, minus little f of 0, okay? Right? And so if we think about it, right? So if we think about the fact that our Laplace transform for our step function is nothing more than e to the minus as divided by s, okay? Right? So if we took the derivative of our step function, we just essentially end up just multiplying it by s, right? So we have s times e to the minus as over s, right? Minus the step function evaluated at 0. Most of the time, your step function is not going to be at 0, so that's going to be 0, okay? So if we plug this in for f of s up here, we get e to the minus as, right? Which is the Laplace transform of the derivative of the step function, right? Which, as we know from the previous, just like 10 minutes ago, that is also the Laplace transform of our impulse function. Okay, so step functions, impulse functions are connected by their derivatives. All right, so we're not going to do too much with this fact. Essentially, we're just going to be solving differential equations. But I think it's kind of a neat thing to share that they're so closely related.
Is that minus?
No, it's an equal sign. So, or you mean here?
Yeah, you just
U of t minus a. Yeah. Mm-hmm. All right. Any questions before we jump into an example? Okay. All right. So let's do an example. Okay. So in this example, we're going to do basically we're going to model a hammer blow on a mass spring damper. Okay, so we have our differential equation here. So we have d squared y dt squared plus 3 dy dt plus 2y is equal to delta t minus 1. Okay. All right, so you can see here that we have the only forcing function that we have here is just a hammer blow that's occurring at t is equal to 1. Okay. Okay. Right, so you can think of this as kind of a delayed hammer blow. So it's not one that happens right away. Okay. And then let's put some initial conditions on this. So we're also going to say that y of 0 is equal to 0, and then dy dt at t is equal to 0 is equal to 0. Okay, so we're going to assume our system starts from rest. The only forcing is going to come from that delayed hammer blow at t is equal to 1. Okay. All right, and so from this situation here, we aim to find the solution or the expression for y of t. Okay, so we have a fairly straightforward differential equation here with our impulse forcing, right? And so because we have that impulse function on the right, the only recourse or the only way that we can solve this is through Laplace transform. Okay, so let's go ahead and start. So we start with this problem like every Laplace problem that we have. So we're going to take the Laplace transform of this entire function. Okay. Okay, so we're just going to take the Laplace transform of every single term. So we're going to start with the second order derivative there. Okay. So that's going to be s squared times y of s minus s times little y of 0 minus dy dt at t is equal to 0. Okay. So that's the Laplace transform of our second order derivative term, d squared y dt squared, plus 3 multiplied by the Laplace transform of dy dt. So this is s times y of s minus little y of 0. Okay. Plus 2 times y of s is equal to. Now our forcing function. So we have an impulse function that occurs at t is equal to 1. And so the Laplace transform of this is going to be e to the minus s. Okay. All right, so let's go ahead and plug in our initial conditions, right? And so our initial conditions in this case are pretty simple. So there's 0 everywhere. So basically anywhere we see initial conditions, we're just going to go ahead and 0 those out. Okay. All right, and then all we're left with is y of s multiplied by s squared plus 3s plus 2 is equal to e to the minus s. Okay. All right, so now that we have it in this form, we can go ahead and solve for y of s. So y of s is equal to e to the minus s divided by, I'm going to go ahead and factor this this function already. So this is just s plus 2 times s plus 1. Okay. And that is our y of s. All right. So then the last step, we need to invert this, right? So we've already solved for y of s, but now we just need to invert it to something that we can do in the table. But before we do that, we need to do partial fractions. Okay. Because right now that that quantity is not something that's in our table, so we need to do partial fractions in order to get there. Okay. And remember our rules with shifting, right? So whenever we have a shift, like that, like e to the minus s, we ignore it first. We take the inverse of the base function and then apply the shift after. Okay? So we're going to do partial fractions, but we're going to ignore the shift for now. Okay. All right. So we have 1 divided by s plus 2 times s plus 1. Okay. We're going to split this up. This is going to be a over s plus 2 plus b over s plus 1. Okay. All right, so you know the drill from here. So let's go, we're going to go ahead and multiply this by the complete denominator. So we're going to multiply by s plus 2 times s plus 1. Okay. On the left-hand side, that's going to give us 1. On the right side, we're going to get a multiplied by s plus 1 plus b multiplied by s plus 2. So let's go ahead and distribute and group the like terms. And so we do that, we get a plus b multiplied by s plus a plus 2b. All right, and so this is a fairly simple system to solve. And so, just like we normally do, let's go ahead and equate the terms on the left and right side. So for the s term, we have 1 is equal to a plus b. And then for the constant term, we have, for the s term, we have 0 is equal to a plus b. Right, there's no s term on the left-hand side. And then for the constant term, we have 1 is equal to a plus 2b. All right. So this is a fairly simple system to solve. So we're going to take the first equation. We're going to say that A is equal to minus B. Okay, so all I did is subtract B from both sides on the first equation. Let's go ahead and plug that into the second equation. Okay. All right, and so we plug that in, we get 1 is equal to minus B plus 2B. Okay. So minus B plus 2B is just a positive B. And so this is B is equal to 1. And then we plug that into our original equation, we get A, then must equal to minus 1. Okay. And so we go ahead and apply that partial fractions, and finally we get 1 over S plus 1 minus 1 over S plus 2. Okay. Right, so let's go ahead and plug that into our Y of S. All right, so then we get Y of S is equal to e to the minus S multiplied by 1 over S plus 1 minus 1 over S plus 2. Okay. All right, any questions on how we got to this point here? Okay. All right, so from here, it's pretty straightforward. So let's go ahead and take the inverse, right? So remember, but we have a shift here, right? So let's ignore that shift first, and let's inverse the base function inside. Okay. So let's inverse. We're going to ignore the shift. Okay. So we get Y of t is equal to e to the minus S multiplied by Laplace inverse of 1 over S plus 1, that is e to the minus t, minus 1 over S plus 2, that inverse is e to the minus 2t. All right, and so now that we have the inverse Laplace, we have our function of time. Last thing is just to apply the shift. Okay. And so we apply the shift, we get Y of t is equal to, we're basically going to shift everything over by 1. So we have e to the minus t minus 1 minus e to the minus 2 t minus 1. Okay. And we need to multiply by our step function, u of t minus 1. All right. Well, yeah, fairly straightforward, right? And so the nice thing about impulse functions is that, you can see that our Laplace transform for our impulse is one of the rare Laplace transforms that actually don't contribute anything to the denominator, right? So it's the only Laplace function which only has a numerator term. And so that actually does not, it doesn't complicate your partial fractions. Whereas, step functions or any other forcing functions, it's going to make your denominator a lot more complicated. But impulse functions don't do that. Impulse functions just, they don't contribute to the denominator. So even if you do have to do a partial fraction decomposition with an impulse function, it's usually pretty light, like it is here. Okay. All right, so let's go ahead and do another example with impulse functions. Okay, this one's a bit more physical, or I guess a bit more tangible, I can say. So another really interesting engineering application that has this impulsive forcing is combustion reactions. Okay. So if you're not familiar, a combustion reaction is basically just the combination of fuel and air and oxygen and some kind of spark, right? And so you essentially create a little miniature explosion, right? Okay, so we're going to explore basically the sudden heating that comes from a combustion reaction. Okay, so let's draw our chamber. A very simplistic chamber. So combustion chambers don't actually look like this, but it's the best I can draw from here. Okay. And so inside the chamber here, we're going to draw basically the result of fuel, oxygen, air, and a spark, right? So essentially we have a little miniature explosion. Okay. All right, and so that explosion, of course, is going to release heat, right? And so by by producing this combustion reaction, there's going to be a rise in temperature of the chamber itself. Okay. But the amount of heating that it actually gets from the combustion reaction actually only occurs over a very brief period of time. Right? Unless you have additional fuel inside the combustion chamber where it can kind of light fire and produce more heat, right? In most combustion chambers, you don't want that to happen. So your little explosions or little combustion reactions are often very controlled and only occur over a brief period of time. Okay. And so at the same time, right? So at the same time, while the combustion chamber is being heated by the combustion reaction, you often have some kind of cooling that occurs on the outside. So let's say that we have some convection cooling on the outside. So we have some air or fluid that's kind of moving past the chamber. All right. And so, this kind of brings us back to, maybe the first or second lecture that we ever had in this class, where, we can modify the convection cooling of a material using what's called Newton's law of cooling. Okay. And so that cooling is going to have some convection coefficient H. Again, don't worry exactly what H is, just for our intents and purposes, H is just some number. And H is basically going to be a parameter that, the higher it is, the stronger our convection cooling is going to be. Okay. And then T infinity, we're not actually going to use T infinity in the calculations, but T infinity is the ambient temperature, the temperature of the air. Okay. All right, so very long-winded explanation of this, of this example here, but I think most people probably aren't taking heat transfer right now, so that's why we went through the whole thing. Okay. Okay, so let's go ahead and write an expression for the temperature of the chamber. You're going to see that the explanation is actually longer than the solution, right? And so for a convection cooled situation like this, we have a first order differential equation. Okay, so we have dt. Okay, so for big T is the temperature, middle T is time, plus H times T is equal to delta T minus 3. Okay. So once again, right? So once again, we have a direct delta function or impulse function modeling our forcing, and it's delayed, right? And so it's going to be delayed at T is equal to. Okay. Okay. And then we also need an initial condition. So since this is a first order equation, we only need an initial condition on the temperature, not the derivative. And so we say that T of 0, let's say that it has some initial condition. So let's say it starts at, we'll say it starts at room temperature. Okay, actually we have T infinity there. Let's use T infinity. Okay, so let's say that the initial temperature of the chamber matches that of the surrounding air. So T of 0 is equal to T infinity. Okay. All right. And so based on all this information here, we want to find an expression for T of T. Right. So essentially this is asking us to solve the differential equation for the time evolution of the temperature. All right. Any questions on the setup for the problem? All right. Good. All right. So this is pretty straightforward. So we are just going to solve this with Laplace, right? So we're going to take the Laplace transform of this entire expression here, because we have that delta, right? And so we don't have any other way of dealing with an impulse function other than Laplace. All right. So let's take Laplace of the entire expression. All right, so this is actually pretty straightforward because we just have a first order equation here. So we're going to have S times T of 0, T of S minus T of 0, okay, plus H times T of S is equal to E to the minus 3S. Okay. So since our impulse function is delayed by 3, that means we have an offset of 3, so that's E to the minus 3S on the right-hand side. Okay, let's go ahead and plug in for our initial condition. So our initial condition here is T infinity. So we have, let's see, let's solve for T of S. And so we have S plus H times T of S minus T infinity is equal to E to the minus 3S. Okay. Okay, so let's go ahead and move T infinity over to the other side. So you have S plus H multiplied by T of S is equal to E to the minus 3S plus T infinity. Okay. All right, so now that we have it in this form, we can just easily solve for T of S. And so we're just going to divide both sides by S plus H. Right, so we solve for T of S, we get T of S is equal to E to the minus 3S divided by S plus H plus T infinity divided by S plus H. Okay. Okay. And then from here, we just have to inverse it. And luckily for us here, there is no partial fractions that we have to do because the only denominator term that we have is just S plus H. And so that's something we could invert directly from the Laplace table. Okay. But we do, even though we don't have to do partial fractions here, we do have a shift, right? So let's ignore that shift just like we normally do. So we have T of T is equal to inverse Laplace of 1 over S plus H is E to the minus H times T. Okay. Multiplied by E to the minus 3S plus T infinity E to the minus H times T. All right. And then finally, last step in this problem is we just have to apply that shift. Okay. So we only have a shift on that first term. The second term with the t infinity, we don't have a shift there. Okay. So we have t of t is equal to e to the minus h times t minus 3 multiplied by u of t minus 3 plus t infinity e to the minus h times t. All right, so pretty straightforward, right? So with only a first order equation here, there's no need for any partial fractions. It's a very straightforward kind of problem to do. Okay. Any questions on this? Okay, all right. So technically, that's the end of my lecture notes on Laplace transforms, and so this is technically the cutoff for midterm 1. We do have 30 more minutes though, and so I did want to do a couple more examples just to kind of give you guys a bit more practice. Okay. But technically, that's the end of the lecture, and so if you wanted to take off, you're definitely more than welcome to. Well, I guess you could technically do that whenever, but if you want to stick around for a couple more examples, they do have some more for that. Great. Okay, so these examples are also published online, and so this is not something I'm making up that here. So there are documents for this, and so the document for this I think is lecture notes 4A, and so the document's called More Laplace Examples with Step and Impulse. So very kind of straightforward. Okay. So first, new example that we're going to do, we're going to take a step back. So we're going to go back to step functions, because I think that one's the bit more challenging one. Okay. We have y double prime plus y prime plus 5/4 times y is equal to g of t, where g of t is a piecewise function. Okay. So g of t is going to have a value of sine of t when t is between 0 and pi. Okay. Right, and then for all values of t greater than pi, our function here is going to be 0. Okay, so basically this function is going to go through one cycle. I guess that can be 1/2 cycle of sine, and then go back down to 0. Okay. All right, and then we have our initial conditions. And so we have y of 0 is equal to 0, and then y prime of 0 is equal to 0. Okay. Okay. So first thing you should note, I've been trying to, do it the other way this whole class, but this is the prime notation for derivatives, which I'm sure you guys have all seen. So y prime is the first order derivative, and y double prime is the second order derivative. Okay. Okay. So let's go ahead and solve this problem using Laplace. All right, so first step in these type of problems, whenever you have a forcing function that's defined in a piecewise manner, we do have to express that forcing function using our step functions. And so the idea is to get g of t, or our forcing function, into a single expression where we can easily take this Laplace transform. Okay. So you have g of t. So this one's pretty straightforward. We just have basically one section of the function that we turn on initially, and then we shut it off at t is equal to pi. So this is equal to sine of t multiplied by u of t, right? So that's when we turn the function on. So we turn the function on at t is equal to 0, and then we turn the function off at t is equal to pi. Right? This is minus u t minus pi. Okay. Yep. All right, and then we can go ahead and take its Laplace transform as well. Okay. But first, first we need to distribute this through. Okay, so let's distribute this through. So we have sine of t times u of t minus sine of t u of t minus pi. Okay. All right, so we want to take this Laplace transform this, right? So for the first term, we don't have any issues because we have sine of t and u of t. And u of t is essentially just one, right? And so that's no problem. Okay. So we take the Laplace transform of this. All right, we just get the Laplace transform of sine of t, which is just 1 over s squared plus 1. Okay. Now we take the Laplace transform of the second term here, okay? Right? We run it into a little bit of an inconvenience, right? Not really an issue, I'll call it inconvenience, right? So we want to take the Laplace transform of something that has a shift, right? So the u of t minus pi, that's telling us we have a shift in pi. Okay. Now, if we were to take the Laplace transform of this, we would require our function to have the same shift, but it doesn't, right? And so we have sine of t. This does not have the same shift. Okay. And so before we can take the Laplace transform, we do have to, apply for shift here. Okay. Okay. So remember what we do in these situations. So, we have a shift of pi. And so in order to apply our shift, we're basically going to replace our t in our function with t plus the shift. All right. So that was kind of the application or kind of the twist on the second shifting theorem that we've talked. I think probably not, maybe not last Tuesday, but probably the previous Thursday, so about a week. Okay. Okay. All right, so let's go ahead and do that. So this is going to be, we're going to take the Laplace transform of sine of t, u of t minus pi, right? So I'm just kind of rewriting what we have above, okay? And so applying our shift, we essentially get e to the minus pi s on the outside, multiplied by the Laplace transform of sine of t plus pi. Okay. Where we replace t with t plus the shift. So t then becomes t plus pi. Okay. And we want to take the Laplace transform of this. Okay. Okay. Now, we do need to know our trig rules a little bit in order to take the Laplace of this. But this one, I would argue, is not that bad. Okay. Because we're taking a sine and we're essentially shifting it to the left by an amount of pi, right? So pi is a half cycle, right? So we're 2 pi is the full cycle, right? So, just because of the periodic nature of sine and cosine, so we have sine of t plus 2 pi, right? So we basically repeat a whole cycle. We know that this is equal to sine of t, right? Just because the value of sine, cycles every 2 pi. Now, sine of t plus pi, that's a half cycle, okay? So actually what we get from this is not sine of t, but actually minus sine of t, okay? Because if you plot out, sine of t, right? Right, so sine of t starts out at 0. Looks like this, right? For one cycle. Basically, if you take any point and you shift it up by a half cycle, so let's say we take a point right here, okay, and we shift it over by an amount by a half cycle, okay, we basically end up with a value that has the same magnitude but opposite sign. Okay, so sine of t plus pi is actually equal to minus sine of t. Okay, so that's actually pretty convenient for us. So let's go ahead and plug that in, right? So now we have minus e to the minus pi s, Laplace transform of sine of t. We know the Laplace transform of sine of t, we just found it. And so this is minus e to the minus pi s multiplied by 1 over s squared plus 1. All right, so now we can take this and plug it back into our g of s. Okay. Okay, so there's a little bit up there, but basically we're going to take this and plug it in for this right here. Okay. So there's a minus sign here that I kind of forgot about, so that, we do have to account for that. And so we have a minus sign right here and a minus sign that comes out from the Laplace transform. And so those two things are going to cancel out. Okay. And so what we get is we get our g of s is equal to 1 over s squared plus 1. So that was the Laplace transform of the first sign term that we had in our expression there, plus e to the minus pi s divided by s squared plus 1. Okay. And of course, you can simplify this. Well, we don't have to simplify. We can just kind of keep it as is. Okay. So this is an interesting case, an interesting application of our second shifting theorem combined with some knowledge of our trig, our trig functions. Okay.
We're not doing the e's of minus t.
We do have it on the second. Yeah, we have the e to the minus pi s. All right, any questions on how we got this this function here? Okay. All right, so let's go ahead and apply it to our Laplace transform, or Laplace of our entire equation. So let's go back to the differential equation and take its Laplace transform. Okay. All right, so we have y double prime plus y prime plus 5 over 4y is equal to g of t. Okay. So we're going to take the Laplace transform of this entire thing. Okay. Okay. And let's remember y of 0 is equal to 0. Y prime of 0 is equal to 0. Okay. Okay, so we take its Laplace transform, we get s squared big Y of s minus s little y of 0 minus y prime of 0 plus s multiplied by y of s minus little y of 0 plus 5 over 4 big Y of s, okay. And that's equal to g of s. Okay. Right, we just solved for g of s, but we'll wait until we have more room to kind of plug it in. Okay. All right. All right, so next, let's go ahead and plug in our initial conditions. And so we know that our initial function value is 0. We know our initial derivative is 0. So that simplifies things for us. And so I'm just going to cancel out all of these guys here. Okay. Right, and so all we're left with then is y of s multiplied by s squared plus s plus 5 over 4, okay, is equal to g of s, where g of s is, I will factor it actually. So let's do 1 plus e to the minus pi s divided by s squared plus 1. Okay. All right. So next thing, of course, is we're going to solve for y of s. And so we're going to divide both sides by that quadratic expression. Okay. So we get y of s is equal to 1 plus e to the minus pi s divided by s squared plus s plus 5 over 4 multiplied by s squared plus 1. Okay. Alrighty. Okay, so just you know, in the whole sense that all things must be balanced, right? So we've gone through a couple examples today where our partial fractions was not bad. Well, this is about as bad as it gets for partial fractions, and so let's just kind of dive into it, right? Okay. All right, so let's do our partial fractions, and I'm only going to do it once, right? I'm only going to do it for the one in the numerator, because the other one, the e to the minus pi s, that's essentially the same as having a one in that numerator. It's just that we're going to apply the shift after, but the partial fractions is going to be the same for both. Okay, so we have 1 divided by s squared plus s plus 5 over 4 multiplied by s squared plus 1. Okay. And so we can only break this up into two terms because we essentially have two quadratic functions that we can't factor anymore, right? So we're gonna have an as plus b divided by s squared plus s plus 5 over 4 plus cs plus d divided by s squared plus 1. Okay. All right, so a little bit of a mess, but remember, you know, when you have a quadratic function in the denominator, your numerator has to have the power of s that's one less than denominator. So that's why we have a linear function in the numerator for both of these terms, right? So we have as plus b over the s squared plus s plus 5 over 4 plus cs plus d divided by s squared plus 1. Okay. All right, so you know the drill at this point. Let's go ahead and multiply by the denominator. Okay. All right, so that gives us 1 is equal to, we have as plus b multiplied by s squared plus 1 plus cs plus d multiplied by s squared plus s plus 5 over 4. Okay. By the way, something like this, you know, probably is a bit too intense for the exam. So don't worry that we're not going to have a partial fraction this bad on the exam. Okay. But it's good practice, right? It's good to look at something like this just so that, you know, if you can get this one, you can do this one, then you'll definitely be good for the exam. Okay, so let's go ahead and distribute these out. So we have quite a bit of foiling that we need to do. Okay. Actually, we have 1 is equal to, I'm just going to go one by one here. So we have as squared plus as plus, or excuse me, as cubed plus as plus bs squared plus b. Okay. Plus, we have cs cubed plus cs squared plus 5 over 4 cs plus ds squared plus ds plus 5 over 4 d. Okay. Typically on my exams, I like to have one long question. So part of the trick is to identify what that long question is. And I'll tell you right now, the long question is not a partial fraction. I'll tell you that. Okay. All right, so we've gone ahead and distributed everything. Let's go ahead and group the like terms. Okay. Okay, so first we have our s cubes. And so we have s cubed multiplied by a plus c. Okay. All right, then we have our s squared terms. What do we have for s squared? We have b plus d. Okay. Next we have our s terms. Oh, we have a c, excuse me. B plus c plus d. We have our s terms. So for s, we have a plus 5/4c plus d. And then for our constant term, we have a b plus 5/4 times d. All right, and so now we can go ahead and set up our system of linear equations. So let's go ahead and do that. Okay, so we have s cubed, s squared, s, and our constant term. Okay, so for s cubed, we have a 0 on the left-hand side, and that's equal to a plus c. For s squared terms, we have 0 on the left-hand side. That's equal to b plus c plus d. Okay. For s terms, we have a 0, and that's equal to a plus 5/4c plus d. Okay. And then finally, our constant terms, we have 1 is equal to b plus 5/4 times d. Okay. All right. So not an easy equation to solve, right? So there's nothing kind of obvious for us to kind of plug in and solve here. Probably what I do is that I would try to, try to eliminate each of the variables one by one. And so I'd use equation 1 and equation 4, just because those equations only have 2 variables in them. And I plug in for b and c, maybe in another equation, and then use that to solve for d. Okay. Okay. But just for the sake of time, let's say that we solve for the solutions for this. And so what we get from this is a is equal to 16/17. B is equal to 12/17. Okay. C is equal to minus 16/17. And D is equal to 4/17. Okay. Well, nothing on your guys' homework, but just for this. There might be one on the homework, I guess. Okay. All right, so let's go. You can go ahead and plug these in. And so we plug that in, we get. Okay. So we have 16/17 times s over s squared plus s plus 5/4 plus 12/17 multiplied by 1 over s squared plus s plus 5/4. Okay. Minus, let me just continue right here. 16/17 multiplied by s over s squared plus 1 plus 4/17 times 1 over s squared plus 1. All right. So that right there, that is our y of s. Okay. We've separated this as best we can, so we've done our partial fractions, and so now all that's left is to invert each of these terms. Okay. Now, a couple of these terms they're basically ready to invert, right? And so we look at this term, we look at this term, right? Those are ready to invert because those already match up with something that we have in the table. These are basically just straight up cosine and straight up sine with a constant in front. Okay. So this term, you invert it, you get a minus 16/17 cosine of t. And then this term right here, this is equal to a positive 4/17 sine of t. Okay. All right, and so that is that's good. So that's already half of our inverses. And so the only ones we have to deal with now is the ones with the quadratic in the denominator. Okay. And remember the way that we deal with these, right? We have basically a quadratic function that we can no longer factor. Right. So the only option here is that is to complete the square. Okay. And so the hope is by completing the square, we end up with something where we can invert it from the table because we'll end up with an exponential multiplied by a sinus. That's where we're hoping to go. Okay. Okay. All right. So we have s squared plus s plus 5 over 4. Okay. So we're going to complete the square on the first two terms there. Okay. Okay. So we complete the square. We can basically see that to complete the square, we're going to add 1/4. Okay. Because we have s squared plus s plus 1/4. Okay. This is the square of s plus 1/2 quantity squared. Okay. Right. So how did I know that? So I knew that because we have this second term is s, right? So the coefficient in front of s is 2 times whatever this coefficient must be right here. Okay. Right. So I knew that the square that we need to complete is s plus 1/2 squared, just because we had an s squared plus s, right? And so I just basically added the 1/4 there in order to complete that square. Okay. Now to complete the square, we also need to subtract it as well. Okay. And so we're going to subtract a 1/4 from that. Okay. And then we're going to add that to the 5/4. And so we do all that. Then our denominator then becomes s plus 1/2 quantity squared plus 1. Okay. So we very quickly ran it. I thought we would have enough time to finish this, so I apologize. But let me go ahead and just outline the rest of the steps just so that you can see. And remember, the document for this is online too, so all the steps are outlined in that extra document. I have one more example in here as well. Okay. All right, so we go ahead and replace our denominator by this. So we have a 16 over 17 multiplied by s over s plus 1/2 quantity squared plus 1 plus 12 over 17 times 1 over s plus 1/2 squared plus 1. Okay. So we're almost there, right? So the only thing we have to do before we invert is we need to manipulate the numerator of our cosine term, right? So remember, in order for us to invert, right, we're essentially inverting with the first shifting theorem. And so we basically need to invert this by making sure that our numerator matches the shift of the denominator. Okay. So essentially, you need to perform a little bit more algebra to get s plus 1/2 up top, right? And then you can invert that. And so that's, of course, going to affect the coefficient here as well. Okay. All right, so I apologize. I thought I could finish this example, but time just went by so quickly. But let me go ahead and draw a line here. Okay. So this line here, this is when midterm 1 stops. Okay. So anything that we go over in class after that line is not going to be on midterm 1. So Tuesday, we're going to start something new, right? So Tuesday, we're going to start to go over vector calculus, but vector calculus is not going to be on the exam, right? So today is kind of the cutoff for midterm. Okay. And remember, midterm 1 has been pushed back. So midterm 1 is going to be on Tuesday, March 10th. So that's not next Tuesday. That's the following Tuesday after that. So you have about 10 days to study for midterm 1. Okay. All right. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys next week.
Yep.
Yep.
Do you have any more problems like the homework stuff? Yeah.
Yeah. So I posted additional Laplace problems. So I have one document for additional step and impulse problems. And I have another document on additional Laplace problems in general. And there's also additional problems just in the base lecture notes. I didn't have time to go over in class. There's a lot more there. Yeah, and that's true for the first order equation, second order equations.
And those are gonna be engineering oriented, not just the simple math.
There's a mix of both. So there's some where it's just the math, but then I have a couple in there that are engineering. Yeah.
Thank you.
Yeah. YouTube.